application programming interface comes in different forms. When developers get down to building a web API, first they decide which specification to use. Most of the time, they go for REST. But, analyzing their product requirements, a tech team can come to the conclusion that the solution calls for another approach. In this video, we're going to review the 4 major web APIs that support communication between clients and servers. Comparing web API types: SOAP, REST, GraphQL, and RPC. The earliest and simplest form of API was Remote Procedure Call, or RPC. The name speaks for itself. It's a straightforward interaction where a local client sends commands to a remote server. Here's a closer look at how it works. Both client, say an application, and server use different call parameters, so they must be converted to be understood on the other side. These parameters conversion is performed by dedicated pieces of code called stubs. So, when a client calls a server via an RPC API, a client stub converts parameters used in the function call. Then, a server stub deconverts them on its side and executes the function. After the server stub converts the result back for the client, a client stub deconverts them. The RPC pattern has been around since the 80s. RPC started with XML and later JSON-based versions. But in 2015, Google came up with a general-purpose RPC, or gRPC. Today, massive systems like Facebook's Apache Thrift and Twitch's Twerp use nothing but gRPC for their internal microservices communication. As microservices exchange tons of calls per day, it takes a really high-performance API to optimize the network layer. And RPC style, with its short, lightweight messages, goes easy on the network. In 1999, a year after the XML RPC was created, Microsoft scrubbed it away with SOAP, Simple Object Access Protocol. XML RPC had a con that had to do with XML itself. It didn't distinguish between different data types, so developers had to add additional metadata to label a field with a data type. Aiming for consistency, SOAP carved the format of the transmitted message in stone. Was it informative? Indeed, but it was also verbose. A SOAP message is framed with an envelope tag. Envelope, a root element of every SOAP message, starting and ending it. Then follows header, its optional sub-element. A header is filled out with any application-related specifics or extra requirements necessary for message processing. Now, the body contains the request or response to the recipient. If request processing fails, the response will also include the fail element, describing an error that occurred. Although many developers shudder at the idea of having to deal with a SOAP API, we can't ignore it. SOAP is still sticking around for a lot of financial services and corporate systems like Salesforce. That's because it has a couple of tricks up its sleeve. Security. SOAP WS Security Extension encrypts a message and puts a lock on it, so only a recipient with a security token is able to pass authentication and access the body. What's also important is that SOAP operations can chain messages to keep the server aware of the previous requests. Storing all the received information goes heavy on the server, but it's necessary for complex transactions where multiple parties are involved. Take a flight booking process. A SOAP API memorizes the flight dates you're looking for, and after the second request, it provides information on pricing. SOAP has another trait, a tight coupling between a server and a client. If you need to update message properties, you have to make changes both to the server and the client. In the 2000s, the web started changing. It required a lightweight, uniform, and flexible way for different systems and services to communicate. But SOAP was verbose with its XML message structure and inflexibility. This was the moment when representational state transfer, REST, appeared, and for some time it was used in parallel with SOAP. But soon, REST won the popularity contest. The RESTful approach drastically differs from SOAP. First, it's resource-based. SOAP and RPC use different commands or verbs to manipulate the service. REST focuses on resources, actual data, but it keeps verbs to a minimum using HTTP methods: get, put, post, and delete. And it's much easier than using numerous methods required to operate SOAP and RPC APIs. Second, instead of a fixed and rigid structure of SOAP, REST suggests constraints. It sets boundaries that shouldn't be crossed. Let's start with the client-server autonomy constraint. REST says that clients and servers don't care about each other's internal parts. As long as the interface between a server and a client is not altered, they can undergo various changes and it won't affect their communication. But the interface itself must remain the same. This brings flexibility so lacking with SOAP. So another constraint is a uniform interface, which means a consistent representation of resources to clients, with uniform guidelines throughout the system. One naming convention, one data format, and one endpoint format. An endpoint is the actual address of the resource. Its URIs together with an HTTP method that operates the resource. The main ones are get to retrieve, post to create, put to update, and delete to erase a resource. Uniform interface helps developers grasp the logic of an API once and then apply it with other APIs as well. The REST style also suggests a layered system architecture. Take a classic three-tier architecture where a client makes requests to the application server that forwards them to the data server. Calling a server, a client doesn't know whether it's the end server or an intermediary along the way. A server can hide a set of other servers behind it. These services take part in producing a reply to the client. But a client calls this particular contact server that aggregates the reply for the client. So a client doesn't care what's behind the interface. It only knows how to process the message that a contact server returns. This allows for a greater scalability on the server side. The fourth constraint is stateless interactions. Treating every request as new, the server doesn't store any info related to the previous session. Such session independence is just the opposite of what we've described in SOAP. But SOAP supports both types of interactions. Number 5 is caching. REST APIs use HTTP caching, so clients can retain content and reduce the load on the server. Code on demand is the last and, frankly, rarely used architectural constraint. A good use case for code on demand can be a secret chat in a messenger. To encrypt communication, a client asks for a key-generating code that resides on the server side. The REST API fetches the code and runs it on the client side. So the server isn't aware of the encryption key used in this process. These constraints enforce simplicity, so it's really easy to write API code. But you may have to violate one or two of them in cases where the business logic of your application and the constraints cannot coexist. No worries. Your API will still be RESTful, just not 100%. Now, to the fly in the ointment. REST APIs can be too chatty. Clients have to make a number of separate calls to different resources to collect the result. But in addition to the relevant data, they also download lots of unrelated info. Let's say we want to get a name and location of a company as well as its founder's name. To do that, our REST API will make two calls. The first one will fetch all info associated with the company, although we needed only its name and location. The second one will get the full list of data on its founder. The result? It took more time and resources to get our reply than was needed. In 2015, Facebook got tired of REST overfetching data, so they came up with a new API syntax, GraphQL. In contrast to REST, GraphQL makes a single, precise request that returns an all-inclusive reply. In REST, there are a lot of endpoints, and they return some fixed data. So a client has to mix and match those endpoints to eventually get the information for its current request. Now in GraphQL, clients can customize endpoints. How do they manage that? Using a schema. It provides a client with a description of how the data is structured on the server, what resources are available, relations between them, and fields each resource includes. This way, a client understands how to formulate a query that asks the server no more and no less. Back-end developers define a schema up front, and although it's a rather time-consuming process, it pays off later. Making a single query to the server, GraphQL greatly optimizes the payload. That's very appealing for mobile applications. So today, GraphQL is becoming a go-to design for mobile APIs. Speaking of the learning curve, REST is quite intuitive, but you can't jump right in with GraphQL as easily. Prepare to carve out time for figuring out GraphQL niche operations and schema definition language. While GraphQL offers desired features for long-term projects, small and mid-sized ones don't need to bother and can totally follow the well-known path of REST. Today, you may hear someone referring to REST as rest in peace and cheer for GraphQL. 10 years ago, it was the reverse story, but with REST being the king and SOAP the junk. Yet, we see that SOAP has its niche where it's still being used. Sometimes, API providers offer two API types in parallel. For example, integrating Canada Post services, online stores can choose between REST and SOAP architecture. So don't give in to labeling API designs. Always keep in mind the needs of your software because they will determine your choice. But these four methodologies don't present the full picture of communication between systems. For many years, the idea of an API revolved around a simple logic. A client sends a request to a server and waits to get a response before moving on with other tasks. The server, in turn, must also send a response before going further. Today, an increasingly greater number of engineers argue for an alternative approach, at least in some cases. What if a client doesn't ask a server for information? Instead of asking, "Has the bus arrived yet?" and waiting to get "Nope," and then asking again and again until the bus arrives. Instead, it just posts a sort of a notification with a request message. Let me know when the bus arrives. The bus server is subscribed to notifications from the client. It gets the message and will post a notification that the bus has arrived when it does so. And, you guessed it, the client is subscribed to notifications from the bus server as well. This is known as an event-driven architecture, where event producers and consumers don't directly depend on each other. They act asynchronously and can execute operations when needed, not when the question was asked. It's like the difference between a messenger and a phone call. With software becoming progressively more complex, with many microservices and thousands of events streaming simultaneously, Event-driven communication is what will coexist with traditional request-response methods.